Welcome to this lecture. In this lecture today we are going to talk about a different type of heat exchanger called regenerators. This is basically a storage type heat exchanger, which is in contrast to the recuperators, where we have seen two fluids are flowing either in counter current or in parallel flow, at least to exchange their heat. I mean, hot fluid will be giving heat to the cold fluid, and either it will be a direct heat transfer or it will be separated by a plate or at least some non-permeable medium, and fluids will be exchanging heat. Now, in this storage type of heat exchanger, which we call as regenerators, this is in contrast to that recuperator. It is a storage type heat exchanger, and here if we look into the classification back to our original, originally we have talked about it in some of the earlier classes, and we find that this belongs to according to this, we have here this is the regenerative plate heat exchangers. This is where we have the all kinds of, say, the recuperative heat exchangers like tubular, plate fin, extended type heat transfer, and this is in contrary to that one. We have this regenerative heat exchanger, and this is our different types. We will talk about it in some of the later, in the later slides. Now, what is the basically the difference between this whole class of heat exchangers with this particular type of exchanger is that here we have a kind of same fluid will be occupying the space in different time. What I mean is that by saying so, if we look at the regenerator, this is basically either a fixed bed type or a valve type, and sometime we also have the rotary regenerator. So, here what we find that the hot stream and the cold stream, they are occupying the same bed in different time. So, here if you look into this diagram, this is called the fixed bed or valve type heat exchanger or regenerator. Here we find that this is the hot stream which is flowing through this fixed bed, which is filled with what we call this space as the surfaces as the matrix. So, this matrix we will talk about the matrix in details, what are the type of matrix that is possible. We generally employ for this type of regenerators. And this hot fluid, imagine that the valve is in this position, and in this position the fluid is directly flowing from here and passing through this regenerator. So, it will come out from this and it will go to the process, and while going through this this will heat it up. This regenerator matrix will be heated up. Now, after some time, when this heat exchanger matrix is almost reaching to this hot stream temperature, we know that there would be any more heat transfer possible between this fluid stream and the matrix. So, during that time, what we will try to do is that we will allow this valve to rotate. So, when we rotate this valve, so this configuration will look like this, and this hot stream will now flow through this bed, which is is occupied, or rather this is the matrix which is at a lower temperature. So, this will now be cooled, or rather this matrix will be heated up and the fluid stream will now flow or take this will be also having a changed position like this, and this will come out like this. So, now this hot stream, the role of this regenerator, basically this complete arrangement is to make this hot stream colder. So, what will happen when it flows through this bed which is at a lower temperature? So, it will pick up the cold rather, and it will in turn make this regenerator hotter. So, it will now pass through this configuration. So, ultimately after some time what will happen? Now, this bed was left hot, okay, just in the other previous cycle it was heated up, and then we started diverting the flow through this hot stream through this bed. Now, when it has been diverted, I mean it has been left hot, we really did not put it idle, but what did we do is that we put a cold stream, cold fluid stream through this bed, and this cold stream, what happened? This cold stream is flowing through this bed, and it is picking up that heat which it has left, that hot fluid left, and it heated up this regenerator in the earlier cycle. So, now this cold fluid stream is flowing through this, and it is picking up this one. So, during this cycle, of course, its orientation would be like this, and its orientation will be like this. So, that this passage, I mean this cold fluid usual path is diverted, and this flow is taking place like this, and it is picking up the heat from here, and it is getting warmed. And what is happening to the regenerator matrix? The matrix is getting colder. So, because of this cold fluid stream, we find that the matrix is getting colder, whereas that colder matrix which was there earlier is now being occupied by this hot stream. So, when it is sufficiently cold, we find that there is no heat exchange between this cold fluid stream which is coming at a constant temperature, and it is no more able to pick up heat from this regenerator matrix. We will now switch on, or rather switch the valves in its original position. Now, it will keep on, this hot stream will again keep on flowing through this bed, because this has been become sufficiently colder, and this bed has been sufficiently hot. So, the cold stream will follow this path, usual path, and it will follow this way, but the hot stream will be flowing through this usual path. So, when it becomes again sufficiently hotter, this matrix becomes sufficiently hotter, or this bed is sufficiently colder, and when there is no more heat being exchanged from this, or exchange is possible from this regenerator, we will again switch over to the other configuration. I mean these valves will be changing them from this position to this position, and it will be flowing like this, whereas the hot fluid will be flowing through this bed. So, in alternative cycle, you can see this hot bed is, I mean these beds are remaining fixed, but only thing is that the valves are changing the flow from one regenerator to the other regenerator. So, this is this timing and all we have to find out depending on the flow rate or the matrix or the type of matrix we are using, and we will try to solve some numerical example at appropriate time. Now, looking into the other type of regenerators, this is called a rotary regenerator, where this bed is not, the regenerated matrix is not I mean in a fixed position, rather it is rotating. So, here we see this is the matrix and the other part of the matrix is this one, and we see this is a continuously it is on a shaft, and this shaft is allowing it to rotate like in this direction. So, here we have the cold stream and this is the hot stream. They are flowing through these passages. I mean this passage is meant for the hot stream and this is for the cold stream. So, usually they are flowing in this direction or in this direction. Generally they are in mostly in counter current configuration. Here also we can see that they are in forming a kind of counter current configuration. So, this is the matrix and this matrix is located on this shaft. So, when the shaft is rotating, we find that this matrix which was earlier exposed to the hot fluid will now come in contact when it is rotating. This will come in contact to the cold fluid and it will the cold fluid will be heated up and the regenerator matrix will become colder. So, when it goes again it is continuously rotating. So, it is coming up and it is in contact with the hot fluid and again it is transferring the hot taking that heat from the hot fluid and then in the next it is continuously rotating. So, it will come in contact to the cold stream periodically. So, this periodically hot it is this matrix by rotation it is coming in contact to the hot and cold fluid streams. So, this is in contrary to the fixed bed one, where we have used a valve in a set of valves to divert the flow, where the matrix remained constant or it was remained fixed, whereas in contrast to this one, here the matrix the fluid stream remains stationary, they are not changing its position, whereas the matrix will continuously rotate between the hot and the cold fluid stream to exchange the energy from one fluid to the other fluid. So, these are the basically two primary type of regenerators which we come across in case of rotary in terms of the regenerators. Originally or historically this regenerator has started in 1816 by in an air by Stirling air engine, hot air engine, and gradually it has been adopted in different refrigeration systems. Particularly in cryogenic, we find plenty of application of this regenerative type of heat exchangers. Heat exchangers. In particular, we have seen that there are Stirling cryocoolers, there are GM cryocoolers, there is pulse tube cryocoolers, and all these type of cryocoolers are basically the regenerative cryocoolers, but we mainly use the fixed bed type heat regenerators in those kind of cooling systems. But otherwise in large scale engineering also in the rotary type heat exchangers are in use. So, now if we look into the particularly to the surfaces that are used in this regenerator, particularly we call it as the matrix or the packing geometries, those are used in such kind of regenerators are like this. We can have the cross rod matrices. So, this has been this is one of the very old type of the packing materials, where the random these cross rods or the rods are randomly oriented, and they can also be put in inline configuration, or they can also be put in a staggered configuration, as we have seen. This has been taken from the Case and London's compact heat exchanger book. So, these are some of the primitive type of packing materials or packing geometries meant for these regenerators. Other than that, we have also these oven screen matrices, or this is also used, I mean as regularly we use this type of oven screen for the matrix or regenerated material, packing material. So, the next is another commonly used material is randomly packed spheres or loosely packed spheres. We have the lead or copper shots of particular diameter. Depending on the application, we can use it, say from 2 to 3 mm diameter shots will be there to, as randomly it will be packed in a pipe, inside the pipe, and through which the fluid will be flowing. So, usually what we look for is basically the large heat transfer surface area per unit volume, low pressure drop, and obviously high heat transfer coefficient between the fluid and the material. And of course, we needless to say that it should have a large heat capacity, or the Cp should be high. So, mCp is the heat capacity of this material. So, it should have mass of this this Cp, though we have we do not have any problem with the mass of this material, but as we know that the Cp being function of temperature. So, we have to see or look, we have to be careful, particularly in case of cryogenic applications, that it is having considerable amount of specific heat at low temperature, because we know that the Cp of the material varies with the temperature, particularly at low temperature Cp becomes considerably low. So, we have to take make a notice or take a notice of that one while designing the regenerator for particularly for the cryogenic applications. So, if we now go to what are the formulas, or like what are the correlations that we should use for the packed bed. Here we have packed bed spheres, we have given the correlations. So, here the heat transfer coefficient, as we know that we need to have a high heat transfer coefficient as well as low friction or the low pressure drop. So, it is important to have high heat transfer coefficient and low pressure drop. So, we at least know what are the heat transfer and pressure drop characteristics. Here in this case, in case of packed bed, we have these correlations for the cold. It is given in terms of the cold one J factor, and it is related to the Reynolds number. We will come to the definition of this Reynolds number or the characteristic dimension of this spheres, packed spheres later on. So, here for the Reynolds number, we get RE for RE less than 1000, and also we have correlations available for RE greater than 1000. So, we have these two correlations. Depending on the RE values, we have to use either this one, or we have to use this correlation for the friction factor, and that is, as we know, that it is important for the calculation of the pressure drop. So, now when we go for the heat transfer or the pressure drop calculation, we understand that we have to calculate the Reynolds number, and for the Reynolds number, what is important is the characteristic dimension of the system, and here in this case the equivalent diameter for this packed bed spheres is basically given by dE, or I mean the equivalent diameter. It is defined as the free flow heat transfer, 4 times free flow heat transfer divided by the heat transfer area per unit length, and it is finally correlated to this correlation. I mean, this is where this Ev is basically the void available inside this packed sphere, and then ds is the mean diameter or the average diameter of these spheres. So, this is the average diameter. I mean, there it is not possible that all these packed spheres will be of similar dimension. So, we take the average diameter of this packed spheres, and then we calculate the this void, and we correlate it to this equivalent the diameter of this packed sphere regenerated bed. So, next is when we know the equivalent diameter, we can try to calculate the mass velocity, as we have learned in our in case of the heat exchangers also, that it depends on the mass flow rate, the fluid that is flowing through this packed bed, and the free flow area. Again, it is appearing here. This free flow area now can be correlated to the frontal area and the void. So, this Ev is the void, and Fr is the frontal area of this packed bed. Say if it is a like a tube which is filled with this packed the spheres, randomly packed spheres, and this becomes the frontal area. This cross sectional area becomes the frontal area of this regenerator, and the mass that is flowing in or out, that is the basically the mass flow rate associated with this one. So, we have the mass velocity, we have the equivalent diameter. So, we can easily calculate the Reynolds number for this system. So, now once we have the mass velocity, we can calculate the pressure drop in terms of the Reynolds number, because the Reynolds number can be easily defined on the basis of this mass velocity and dE. And another parameter which will be of our importance, that is the surface area. So, this surface area is basically related to this ds, or the average diameter of the or the mean diameter of the sphere, and this is again correlated to this void, and the V 0 is the volume associated with this regenerator. So, all this will be finally correlated or can be used in appropriate time when we design or simulate these regenerators. So, now with this information, we will now proceed to the other some of the recent or the geometries which are regularly in use, high performance. This is perforated plate. Actually, this is some of the perforated plates, but in case of this is regenerator, we will have only this much. It is particularly this particular perforated plates are meant for 2 fluid stream heat exchangers, but if we remove this portion or if we remove this outer section, this can also be used as a regenerator with appropriate spacers in between the plates. So, this is basically made out of copper, and it is finally it has been coated with silver. So, there is a recent development in the materials science where which allows us to use this metal foam as the regenerator material. Here we have this is often called the metal sponge, and this metal sponge is basically a open porous, or it can also be closed cell. So, basically for regenerative application we use it for, I mean, the open cells are used, and it has different kind of porosity and pore density. So, this is basically by porosity what we mean, that gives the relative density of this material, and the pores, you can understand that these are having larger pores as compared to this one, and these are having still smaller number of pores. So, these are basically these pores are defined as the PPI, pores per inch, and this is nearly about say 5 to 10 pores per inch, whereas this is about 20 PPI and this is nearly 30 PPI. These are copper foams. So, porosity is porosity can be varied between a wide range, and typically of the order of 60 to 65% porosity is looked for the regenerative materials for this when metal foam is used as the regenerative material. So, these are some of the recent addition into this regenerative material packing geometries, but we will now with this basic information go to the analysis part, where we will find that this same matrix is usually I mean the fluid is flowing say in one cycle from this direction to this direction. So, the hot fluid will be flowing from say this direction to this direction, and this hot fluid will in turn heat it up this matrix, and in the next cycle we will find that the cold fluid is flowing through this direction. So, this cold fluid will pick up that heat it has left in the earlier cycle. So, this regenerator is now hot, and the cold fluid is passing through this one and picking up that heat while moving out from this to this direction. So, the same fluid is going in one cycle, leaving its heat over here, and in the next cycle it is moving from this direction to this direction, picking up that heat. So, basically that is how this storage type of heat exchanger works. I mean, it basically allows the fluid to store its energy here, and then in the other cycle it picks up that heat it has left in the earlier cycle. So, that is how it works, but while writing the governing equations, we make it into two parts, I mean for one for the fluid and one for the solid. So, in the solid part we will write this equation, and for the fluid part we write this equation. So, detailed discussion of this equation will be taken up in the next class. Thank you for your attention.